So I wanted to go over these exercises. And exercise 1 is just reviewing some of the symbols that we've learned this semester. And so we see the symbol, which is called mu. It's a Greek letter. Mu stands for the population mean, and that's a parameter. If I could ask every single student at Santa Ana College what their GPA is, I could figure out their mean GPA for the whole population. X bar is the sample mean, and that is a statistic. If it's too hard to ask every single student at Santa Ana College what their GPA is, I could just ask a sample of students at Santa Ana College and find out their GPA, and then I would find the sample mean of my sample. It's a random variable. It's going to be different. We would all take different samples if we were assigned this, and so that's why we can make a sampling distribution for the sample mean, because we all get different numbers. The standard deviation, when we use a Greek letter, is denoted by sigma, and it is also a parameter. If I could, again, find every single student at Santa Ana College, I could ask them their GPA. I could use a formula to figure out their standard deviation. On exercise 2, we're looking at the household size in the United States. It has a mean of 2.6 people and a standard deviation of 1.4 people. What is the probability that a randomly chosen household has more than 3 people? Now, if we read this carefully, just knowing the mean and standard deviation is not enough. We have to know the probability distribution. And since the probability distribution is not given anywhere here, we cannot use the central limit theorem to calculate this probability. And so when we try to figure this out, we realize that just taking a sample of 3 people is not going to be enough. We have to say that this cannot be determined, this cannot be calculated because we don't know the probability distribution. All right. The next problem, what is the probability that a mean size of a random sample of 10 households is more than 3? So 10 households, I'm randomly sampling 10 households, it's more than 3. It sounds like this might be a sampling distribution. Since we're taking repeated samples, everyone's taking 10 different households. But 10 is not enough for us to use the central limit theorem. We need a larger sample. And so in this case, the probability that the mean size of a random sample of 10 households cannot be determined. We don't know the probability distribution. Question C, we know the sample is random and we took 100 households. So we have a sample now of 100 households, which is greater than 30, and it's random. So that means that the central limit theorem, the CLT, the central limit theorem, can be used to calculate this probability. The central limit theorem says the mean of this distribution will still be 2.6. Remember, 2.6 is the mean that is given to us right up here. So the mean of this distribution of sample means, okay, so I'm going to put a little note there that this is the mean of the sample means, is the mean of the population, 2.6. The standard deviation, however, this little symbol here stands for the new standard deviation. It's the old standard deviation divided by the square root of the sample size. The old standard deviation was 1.4. The population standard deviation, I really shouldn't call it the old standard deviation. The population standard deviation is 1.4. The new standard deviation is going to be the old standard deviation divided by the square root of 100. The square root of 100 is 10. And so if I calculate that, 1.4 divided by 10, I get 0.14. You can use a calculator to do this. Take the standard deviation, divide by the square root of 100, and you get 0.14. If I look at the probability distribution, I know that because this is true, because of the central limit theorem, that it doesn't matter if the shape is normal, skewed, binomial, what doesn't matter what the shape is, as long as we have a large enough sample and it's random, the distribution of the samples is going to be normally distributed, centered at 2.6, but I want to find what's the probability that we find an average of 3 people living in a household. So to calculate that probability, to calculate that error, that area, I use the normal app. The normal app says type in the mean, which is 2.6, type in the standard deviation, which is 0.14, and since I'm asked more than 3, I'm going to use upper, and x is 0, x is more than 3, so 3. So I'm going to go to our normal app, I'm going to type in the 2.6 as the sample mean, the expected value of the sample means. 0.14 is the standard deviation of the sample means. Upper tail, I'm going to type in 3 here, 3. And I see that there's just a 0.21%, 0.0021 chance, 0.21% chance. So there's just a 0.21% chance. It would be very unusual to sample 100 households and find that the average is 3. All right, so the central limit theorem requires us to have a sample size that is large enough to find the probability using the normal distribution. Now, if this already said the United States has a household size that is normally distributed, then I could have answered all of these questions, A, B, and C. But since it never told me the shape of the distribution, I have to assume that it could be skewed, and I need a large enough sample to use the normal distribution. And the central limit theorem says if the sample is bigger than 30, then that's large enough. Exercise 3, that's what we're going to do next. Exercise 3 is about federal grant loans. And we see that the grant loans, on average, were $2,600 in the year 2000, 2008. And the standard deviation was $500. So if we pick a random sample of 36 students who got Pell Grants, central limit theorem says that this is normal. This is normally distributed. With a mean of 2,600 and a standard deviation of 500 was the old standard deviation. The new standard deviation is going to be divided by the square root of 36. So the sampling distribution says that the standard deviation gets smaller by a factor of, in this case, the square root of 36. Square root of 36 is 6. So if I wanted to do that, 500 divided by the square root of 36 is 8.33 repeat. 83.33 repeat. All right, so now we know the central limit theorem applies here. We can find probability. Well, let's talk about. We know it's normal, so we know that the highest probability, the highest chance is that a loan would be, a Pell Grant would be $2,600. But we're asked in this case, is it unusual to get a Pell Grant for 36 students, an average of $2,940? Would it be unusual? And of course, if this is unusual, then any student getting more, any sample resulting in an average more than 2,940 would also be unusual. And so I can find the probability by using the normal app. Is this unusual? I want to find the probability that anyone gets $2,940 or more from a Pell Grant. And so I'm going to use the mean of 2,600. I'm going to use the standard deviation of 83.33. And I'm going to use upper. Why did I use upper? Because $2,940 seems unusually high. So I'm using the upper bound to figure out if this is unusual. Upper, all the samples that would have a value of more than 2,940. I'm going to go here. We're going to type in 2,600. I'm going to type in $83.33 as the standard deviation. I'm going to do upper, 2,940. You can see that's way off the charts. $2,940 is way off the charts. So that anything past the second standard deviation is unusual. So that should have been a clue. But the probability here is basically so small that, yeah, it would be unusual. So yes, a sample mean of 2,940 is highly unusual. It is more than 2 standard deviations of average. The probability of this happening, a random chance, is pretty much 0. So it would be very unusual to find this. Now, if we had sampled 100, what is the probability, or how does the probability distribution look? And so if I sampled 100, that's definitely a large enough sample. The center of the distribution, the center, still be at $2,600, but the standard deviation would get even smaller. So remember, it was originally 500. The standard deviation decreases by a factor of the square root of 100. And so if I calculate that, if I use my calculator to calculate that, 100 divided by the square root of 100, I get 50. The standard deviation is 50. So I'm looking for a distribution that has a center of 2,600 and variability of 50. So I'm looking for something that is bell-shaped, something that's centered at $2,600. And then if I go up, this should be 2,650. This should be 2,700. And the very max probably should be 2,750. It would be unusual for anything to be past that. It's possible, but very, very unlikely. I'm going to use the standard deviation to subtract. If I subtract $50, I get $550. I get $500, and then almost all the way out here, the min would be $2,450. And so I'm looking for the graph here that looks most like this distribution I drew here. Right away, I can see that graph D does not have the right center. So that cannot be right. This graph here seems to have values between 2,450 and 2,700, just slightly over 2,700. So that's a possibility. This graph here goes down to almost 1,500. So this graph here, this is 1,500, somewhere approximately. This graph here is having loans, the average loan amount going up to being over 3,500. And so C is just way too spread out. C cannot be the right one since I'm looking for a graph that has loan amounts between 2,450 and 2,750. So it's between these two graphs right here. And we kind of look at the second standard deviation of 2,500. So I'm going to look between 95, almost all the data, 95% of the data should be in this chunk right here. Outliers would be in this area out here. A doesn't have any values outside of those values, but this one here, we see that there are a few values. So 2,500, 2,750 has a few values outside of there. And so B would be the better answer. B would be the better answer since it seems to match up with these numbers here a lot more. That we have a huge chunk between 2,550 and 2,650, whereas here we don't have anyone outside of 2,450 and 2,750. It's just a little too compacted on A.